Morning, everybody. I'm still alive. The rumors of my death have been greatly exaggerated. Even if I did die, I'd still have homework due. I plan on being that teacher from Harry Potter, the history teacher. Isn't he a ghost? Like he died and he just kept lecturing? That's my plan, right? Just be here for forever. It went well. My neck is very stiff and sore, but that's what happens when you get a reverse sunburn. Like range of motion is pretty limited, but that's expected. Over the next 4 weeks or so, as the nerves heal and reorient themselves, I'll get more and more relief. I can feel my fingers again, so that's good. Right? Okay, yeah, thank you. The anesthesiologist told me, because I was talking to him as I was laying there getting ready, I said, what are you going to give me? You going to give me the good stuff? He's like, oh, yeah. So I had, what was it, Versed first, followed by fentanyl. He said it was the good stuff, not the street stuff. He said it was the good stuff. And then I don't remember the third one because by then my memory was erased. So, yeah, good times. Recovering from sedation is not very fun for me, but I got over it yesterday. So, you may not be on very much sleep, and I've been on Versed, so this is going to be a real fun lecture, right? We were doing, I think, the banked turn, right? This idea here. And just to kind of review before we kind of kick it into high gear, we are, like the circle that we're talking about here is a perfectly horizontal circle. This car is going around, okay, a turn. And we've got to lay out all of these forces, and I kind of left off last time with that mind-blowing idea that we've got to find the components of the normal force this time instead of the weight, just because of how our coordinate system is oriented here. Okay, so let's see if we can't write down Newton's second law. Looks like we might have gotten a little started here. We started with the y, like because we knew mg, right, was all in the y. So let's stick with the y direction, this direction right here. So in addition to mg, we also have what? The n cosine theta. So I'm just going to write that over here, not in blue. N cosine theta. Let's do the directions real quick. mg, positive or negative? Pointing down. And n cosine theta? Pointing up. All right. Let's do the x direction. So we're just gonna constrain ourselves to looking along the horizontal here. And as far as I'm concerned, I can only see one force. Right? N cosine theta. So let's just get that one in there, and it's positive because, it's the only thing that's there. Huh? What did we get? Sine theta. I'm going to blame that one on Versed. Recent sedation. Sine theta. Did I get cosine? I got the right one over there. I'll blame it on the drugs, but really, I make that mistake all the time. Okay. We are, what the heck are we trying to solve for? I didn't tell you. We want to solve for like the velocity that the car can safely handle this turn, even if there weren't any friction. Because this problem doesn't have any friction, right? So even if there weren't any friction, what's the safe speed? The like maximum speed you could take on this turn. Is velocity anywhere in any of these equations? Doesn't look like it, right? Looks like we're kind of stuck. Let's dig in a little deeper, though. MAY, what's the acceleration in the y direction? 0. Yeah, we made sure the acceleration was only in the x direction. So that means that we can go ahead and put a 0 right there, which means that if I just do some math, that n cosine theta will be equal to mg. In case we needed that for any reason. We'll find out here in a second. And then what do we know about this MA over here? MAX. What is AX? We don't know its number, but we know something about it. Which way? Inward, towards the center of the circle, right? And we know something about those inward pointing accelerations, don't we? It's equal to the tangential velocity around the circle squared divided by the radius of the thing. So I'm just going to put that in there. And that's how our velocity sneaks in. All right, so if I'm going to solve for this velocity, I need to know what n is, don't I? Good thing I know what n is. mg divided by cosine theta. So if I shove that in there, mg, and then the sine theta divided by cosine theta. And I wrote it that way, special way, because what's sine divided by cosine? It's tangent. Yoo-hoo! All right. Ooh, quick. So we pick that up, but also, do we have an m in every term on both sides? We sure do. So v squared is equal to r times g times the tangent of theta. Does it matter if it's a bus or a sports car? A bicyclist or a rocket? The mass makes absolutely no difference. In fact, what determines the safe speed in a banked turn is the radius of the turn, the planet you happen to be on, and the angle or how banked that turn is. So let's play around with this, right? What if theta were 0 degrees? What would a turn, a banked turn of 0 degrees look like? Just look like flat ground, right? And what's the tangent of 0? 0. And what's 0 times r times g? In other words, on a frictionless surface, can you turn? On a frictionless surface, there's no way. That's how you know the ice skaters in the Olympics are not skating on frictionless ice. Because if they were, everything they could do could only happen in a straight line, right? There needs to be a little bit of friction to be able to turn, okay? What if the angle were 90 degrees?
You would fly into space.
No.
The little acceleration would just fall down.
Nope.
You would turn too far.
What's tangent of 90? It's not 1. It's not 0. Tangent's one of those weird ones. It's infinite. Okay? So how fast is too fast if the turn you're turning on is perfectly vertical? You can go, there isn't a maximum speed. It will always hold you. Okay? There is a minimum speed. That's different. Okay? But this represents maximum speed. So from a maximum speed of 0 on a flat to maximum speed of infinity, if it's vertical, to anything in between. So why do we bank turns? For safety, right? It allows for, if there's a loss of friction in the turn, there is still the ability to keep turning, right? Even if the friction between the road and the car isn't there. Your book, okay, just to be clear, okay, just so you're not too confused, your book says that a banked turns equation is this. Any self-respecting physicist would write it the way I did in the box, because physicists don't like fractions, okay? But again, your book just did what? They just rearranged the equation, right? I just didn't want you to think it was a brand new, different equation. It's not. It's the same thing, right? They just, for whatever reason, they decide to write it like that. All right, so that was, again, an application of circular motion, Newton's laws. And now we need to talk about putting stuff in orbit, because rockets, orbital motion, getting to space, they're all applications of Newton's laws of universal gravitation, which we learned last chapter, and circular motion. What's an orbit? Circles, fields, gravity. Did you know that there are elliptical orbits? Yeah, there are. Okay. There's circular, elliptical, parabolic, and hyperparabolic orbits. But that doesn't really get at what an orbit is. What's an orbit? Kind of this idea of one object going around another. In the specific case where gravity is doing all the turning, isn't it? Okay. So let me find, where's my tennis ball? I apologize today. I cannot get my computer to play videos this morning. Maybe it had Versed also. Okay. So kind of have to describe what's going on here with props. So technically, this tennis ball is in orbit around my hand, right? Okay. And what's the force that's keeping the tennis ball in orbit around my hand? It's the tension in the string, isn't it? Okay. So if we replace my hand with the Earth, and we replace the tennis ball with the moon or a satellite, doesn't matter, okay? Then what's the force that keeps the satellite in orbit around the Earth? Gravity. It's gravity, okay? But gravity, as we know, like if I take this tennis ball and I just throw it up, what's gravity going to do to it? It's going to pull it back down again, isn't it? Okay. So let's answer this question. On the International Space Station, how much gravity is there? Why'd you say that, Griffin? They're floating, aren't they? So if that's the, you know it's the Earth because it's in blue. And because it has a big letter E on it. This drawing is not to scale, by the way. Here's the International Space Station, which to me always looks like a TIE fighter. Okay. So there's the International Space Station. And the International Space Station is in orbit around the Earth. Okay. If we were to calculate little g on the International Space Station, this comes from the last chapter. Do I remember what we got for that? I can't remember what we got for that. Oh, yes, I do. It was big G m over r squared, I think was what we got. And I talked to you about how like little g changes depending on which planet you're on and how far away from the center and all that kind of stuff is. If you, the International Space Station has an orbital altitude of it's like 300, between 370 and 415 kilometers or something like that. If you go calculate little g on the space station, you don't get 0. You get like 8.7 something meters per second squared. It is less than it is on the surface of planet Earth because we're further away from the center of Earth, but it's not 0. So what is going on? Why do we see the astronauts floating around on the International Space Station? Yeah, they're not buoyant because they're not in a fluid. Well, they're in air, but they're not surrounded by a fluid. How many forces act on the International Space Station as it orbits the Earth? 1. 2? Well, okay. Sorry, I was not clear. Ignore the rest of the universe. We're just talking about the Earth and the International Space Station. I know a lot of you are like, what about the sun? What about the moon? What about the Pokemon? Okay, there's lots of stuff out there, right? But which one is gravitationally dominant? The Earth. How do you know? It's in orbit around the Earth, right? Okay. So to be like, if you're doing NASA and you're calculating like spaceflight trajectories to get to Mars, yeah, take into account the sun and the moon and everything else. That's what supercomputers are for. But we don't do that. Okay. So it is just the force of gravity acting on the International Space Station. So what do we call that situation where gravity is the only thing that is acting on the object? Yeah, that's called free fall, right? What's an orbit? It's falling without getting any closer. How many forces are acting on the International Space Station? 1. How many forces are acting on the astronauts inside the International Space Station? 1. Both of them are in free fall. They're falling towards the Earth and not getting any closer. How do you pull that off?
By being on the edge of the gravitational field?
No, the gravitational field is very strong there. Gravitational field is more or less infinite in its reach. Doesn't cancel.
Have some horizontal velocity.
You have to be going sideways. How fast do you have to be going sideways? We're going to find out. But the answer is big number. Most rockets don't take off straight up. If a rocket were to take off straight up, what would eventually happen? It would come straight back down again, right? If you ever get a chance to go to a rocket launch, like see one in person, this is very difficult to understand or even see when they televise a rocket launch. Rockets tend to go up for the first few hundred feet, and then they tip over and start going sideways. They're still going up. Up is important. But you really only need to get up about 100, 150 miles up. Like space isn't that far away. Space is a 1-hour drive at 60 miles an hour. Straight up, okay? It's really not that far away. The problem is that if you don't want to be on a trajectory that brings you straight back down again, you've got to be going sideways fast enough so that if you are in free fall and fall 1 meter down, the surface of whatever you're orbiting has curved away by that same 1 meter in the same amount of time. That's why an orbit can be defined as falling without getting any closer. Sorry, flat earthers. Orbits don't work if the Earth is flat. Okay? They only work if the Earth is round. We need the Earth to be getting out of the way. So when something's in orbit, there is not a tangential force. There's only one force pointing towards the center of the gravitational massive object. Okay? But that tangential velocity allows the thing to fall with the surface curving away by the same amount. International Space Station orbits at about 7 kilometers per second, 7,000 meters per second. That's the same speed as going from New York to Paris in about 5 minutes. Okay, 6 minutes-ish. Okay, so the reason you want to do that way up high is because there's less atmosphere up there, which means less friction. If you try to go 7,000 meters per second at sea level, that's a meteor. Doesn't work very well. Okay, so orbits are a special case of circular motion, and we are going to try and figure out exactly how to do some rocket science here. Okay. Again, I don't have any of my videos working, which is very sad. Oh yeah, I had to pause the recording because I had to, and I don't, yeah, that computer's not going to be able to get it for me fast enough. There's an airplane known as the Vomit Comet. The Vomit Comet. The Vomit Comet is an airplane that NASA uses to train astronauts in weightlessness. Oh yeah, let's get back to this weightless business, right? Astronauts on the International Space Station, do they have weight? Are they being pulled on by gravity? Yes. Okay. So even though it's called weightless, it really isn't. Because what would the International Space Station do if we turned off gravity? If we got rid of gravity, what path would it take? Just a straight line, right? Whatever, just tangentially, it would just start going off. Okay. So that circle is because of gravity. So the space station has weight. The astronauts have weight. It's just they're all in free fall. So let's put this into context. Let's say you're in an elevator and we turn off all the safety systems and we just let you plummet inside the elevator, right? The elevator's in free fall. You're in free fall. How much does the elevator have to hold you up? Not at all. Right? If the elevator's falling and you are falling, is there any reason for there to be a normal force? No, there isn't, okay? And what would it look like from inside the elevator? like you were weightless. Remember we talked about apparent weight, we talked about the roller coaster, now if you get pushed, right? Right? That apparent weight always comes from that contact force, that normal force between objects. Like we think of our weight not as gravity pulling on us, but how much the floor pushes back on us. And that's where that term weightless comes from. Technically, astronauts are in a state of contact forcelessness. But that doesn't sound nearly as fun as weightlessness, right? Okay. NASA tried to fix this a few years ago. They called it microgravity. Still doesn't work because it's not micro at all, right? There's still very much a lot of gravity on the International Space Station. It's just everything's in free fall, so nothing has to hold itself up. So let's get to the vomit comet. How do you train an astronaut about 0G without spending all that money to put them on the International Space Station in the first place? The answer is put them in an airplane. Take a jet, like a standard jumbo, passenger jet. Take all of the chairs out of the middle, okay, and then put people inside without any chairs. Kind of fun. Sounds kind of fun, right? Okay. Fly that airplane and take that airplane off, get it leveled off, and then have it fly a parabolic trajectory that exactly matches the trajectory of, say, a ball being thrown through the air. And if that plane is then flying that trajectory and is in essence following the trajectory of free fall for a thrown object, all the people inside the airplane will experience contact forcelessness. The airplane can do this for about 30 seconds because it has to kind of fly up and then it needs to come down. And one of the very important things about flying an airplane is you don't want to intersect the ground in an uncontrolled manner, right? Okay. Guys, what's the definition of flying? Yeah, throwing yourself at the ground and missing. Okay. So it's not very helpful, but it's still true, right? Okay. So the airplane can fly these paths, but every 30 seconds, it can do the weightlessness for about 30 seconds, and then it has to pull out. It takes about 3 or 4 minutes for it to pull out of the dive, okay? And during that 3 or 4 minutes, everybody experiences 2 to 3 times their normal weight. So they're pinned to the floor. They can't push themselves up because a 180-pound person like me would suddenly weigh about 400 pounds. Okay, so you're just kind of plastered to the floor. So why do they call it the vomit comet? Yeah, okay, because one of the things that most astronauts do the first time they enter this state is hurl, and hurl lots. Okay, why? What doesn't your body like about it? Okay, anatomy and physiology people, right? How does your head know where it is in space?
Because it's attached to your body.
What? Well, but more specifically, you have some holes in your head, and there's some fluid inside those holes, right? Your ear has these semicircular canals that are roughly oriented around an XYZ plane. And if you tilt your head, the fluid tilts in those canals, and that sends signals to your brain about where your head is in space. It works even when your eyes are closed. The main way your brain knows about where your head is in space is where your eyes are looking, okay? But if you close your eyes and you move around, you can still tell where your head is in space because the fluid is moving around in there. It's not as high resolution as your eyes, but it's still a good thing. Anyone that's ever experienced motion sickness has experienced the disconnect between the signal from the fluid in your head versus what your eyes are telling you. And when your brain gets two competing signals from two different systems, it makes only one assumption. Does anybody know what that assumption is? You've got two systems in the body, and they're giving conflicting information. Your brain's evolved one response to that conflict of information. What is it? Throw up. And why throw up?
To reset.
Because poisons and venoms usually cause this. And so poison and venom, what do you want to do with it? Get it out. Okay, now venom technically It's really hard to get out because that means it's been injected somewhere, right? Okay. But poisons typically are ingested, and so the body's reaction to motion sickness is exactly the same one as if you were poisoned. Okay? Just get it out, because out's better than in, right? And so the vomit comet is aptly named because there's lots of baggies on that plane, right? Because they're constantly doing this. They'll do that for like 3 or 4 hours, right? 30 seconds of weightless with 3 minutes of with another set of weightless, right? All trying to get used to that sensation. One of the things that they don't show you on launches with astronauts to protect their privacy is that first few hours after they achieve orbit, they really don't show you what's going on inside the capsule, because most astronauts are just puking their guts out. They get over it after a little while, but what? They usually don't show you very much in that first little bit of launch, because the astronauts are struggling on how to use the toilet in 0G, try not to think about it too much, and they're hurling, right? And vomit in 0G doesn't go down. It goes everywhere. Okay? So, all right. Now you know, and knowing is how you know stuff. For the toilet, yes. No. You can get it into a bag if you're fast enough. The other thing they don't tell you about astronauts very often is that astronauts just wear diapers. Think about it. It's just easier. All right, where were we? Okay, so we did that. We did there's people floating around in the vomit comet. I probably got a copyright strike because it says BBC 2. All right. Okay. Yeah, we got to talk about dudes with collars. We think fashion's kind of funky today. This does not look comfortable to me at all, right? This is their idea of a necktie. Wow. Okay. But who am I to judge a different culture's way of doing things? Johannes Kepler, he came up with 3 ideas about how orbits work. This was before Newton. This is actually a pretty fun story that I don't have time to tell you about, but if you want a kind of a fun ride, go look up the Wikipedia on Johannes Kepler. It involves like kings and deaths and stealing stuff and having to be exiled. It's quite the soap opera. But the upshot is, at the end, Kepler was able to develop 3 laws, 3 observations about how orbits work. And Kepler was the first to do this. He did it before Newton. In fact, Newton used Kepler's laws in order to show that Newton's laws worked. Right? It was kind of the proof that all of these things were working together. The first and second of Kepler's laws are ideas, and then the third one is mathematical. Are you sensing a theme here in physics? Like 2 of them are concepts and 1 of them's math, right? It's kind of the same idea. It's kind of, the universe seems to be kind of put together, at least our understanding of it seems to be put together like that. So let's outline, again, the first 2 are concepts, and the third one holds all of the math. At least Kepler saved the third one for the hard part. The first of Kepler's laws, and this was quite amazing in Kepler's time for him to assert this, okay? But the orbits of the planets are ellipses. The concept of the Earth not being at the center of the solar system was a pretty new idea. Really right up until the Newtonian age, okay? Prior to Kepler, you've got Galileo that's being hauled in front of the church courts for even suggesting that the Earth might not be the center of the universe. Can't argue against data, and the data won out finally. But Kepler comes along and says, yeah, by the way, they're not circles either. Okay, they're actually ellipses. And what's an ellipse? Kind of a weird circle, isn't it? Right? It's a circle that's not the same, so it doesn't have the same radius everywhere, right? Okay. So Kepler, because of his observational data and his kind of number crunching and figuring everything out, finds out that the orbits of the planets aren't ellipses, aren't circles, they're ellipses, and one of the focuses. By the way, both are now considered correct. You could say focuses. There we go. Or you can say foci. Foci if you want to sound Latin. Okay. One of the focuses is at the sun. Okay. So I'm gonna really sort of exaggerate this diagram, but if you have the sun right here, and we wanted to like do the orbit of planet Earth, okay, it might look like that. Now, the thing was, and the amazing sort of result here, is that if we had the ability to like jump in a rocket and fly above the solar system, so like we're looking down on the top of the solar system with the sun and all the planets going around, we would look at the shape of the orbits and we would think they were circles. Like they're so close to circles that you might be like, well, why does it matter, right? Just do circles. And that's what we're going to do in this class. We're just going to do circles. We're not going to do the math of ellipses. But this is important because if you're trying to get to Mars, one of the things that you don't want to do is miss. Because if you miss Mars, where are you now headed? Somewhere else, right? So it's kind of important to know exactly what the orbit of Mars is doing. And it's not doing a perfect circle. It is doing an ellipse. There's a term that's used to describe this, and you might hear this if you're following any kind of, like, we're sending humans to the moon again next month on Artemis 2. And so this is going to come up because their orbit to the moon is not circular. It's actually highly elliptical. It has to be. It's called a transfer orbit. But there's this idea called the eccentricity. If your eccentricity is 0, then you have a perfect circle. And if your eccentricity is 1, then you're in trouble. Okay? This eccentricity of 1 is technically a line. It means that you're no longer orbiting at all. Okay, you're on a path that doesn't take you around something. So like most planets have an eccentricity of like 0.04, 0.03. Like it's the eccentricity is really close to 0, meaning it's mostly circular, right? But if you're really trying to get someplace in the universe, can't just assume circles, even though we will assume circles. A couple other terms to throw at you are perihelion and aphelion. If you see peri in front of a word, that means close. And then if you see like AP, it's really just AP, okay? That means far. And so if I say perihelion, the perihelion of Earth, peri means what? Close. And helios? That's ancient Roman for sun, okay, like the sun. So perihelion, the perihelion of Earth's orbit is the part of its orbit where it's closest to the sun. And aphelion would be furthest point from the sun, okay? If you're around Jupiter, it would be perijove and apogee, because Jove is like the Latin root for Jupiter, okay? So I might slip and say those words instead of closest and furthest approach. Does anybody, while we're talking about it, does anybody know what time of year we are closest to the sun? Here, Earth's orbit. Summer, right? Wrong. Actually, we're closest to the sun about a month ago. It's near the middle to end of January is when we reach our perihelion point, okay? But, Mr. Balogh, that's winter time. Well, not this winter. It's not been winter, right? Typically, December, January, February are cold months in the northern hemisphere. What's going on down south? Ah, it's their summertime, right? Okay, so it must not be seasons, right? In fact, what causes the seasons? It's the tilt of the Earth's axis, okay? This one's hard to demonstrate, but I'm going to do my best with my water bottle, okay? So we're going to pretend like my water bottle is the tilt of the Earth's axis. I'm really going to exaggerate. Our Earth's axis is tilted by 28 degrees, meaning that it rotates on its axis in 24 hours. So if it were straight up and down, it would go around the sun just perfectly straight up and down the whole time, okay? But it's tilted. Again, I said 28, but I'm going to go to 45 just so you can see what's going on. You guys are the sun, okay? All you out there are the sun, okay? And from your point of view, the top and bottom halves of the Earth are equally illuminated, right? Okay? This is spring or fall when we're at the equinox, okay? At the equinox, we have even illumination for the north and south hemispheres of the Earth. But as the Earth rotates around you, the sun, and we go from, say, spring to summer, notice how the Earth's still pointing, its axis is still pointing in the same direction. What side of the Earth do you see mostly? The north, the cap of my water bottle, right? Which means all of the sun's light is directly hitting the northern hemisphere. But it's kind of hitting the southern hemisphere obliquely, or like not quite straight on. So we get summer and they get winter. Okay, we keep orbiting around and we get to the opposite equinox. So if that was spring over there, this would be fall. And what part of the Earth do you see now? Both illuminated evenly. And if we keep orbiting around, going into what is now winter, which part is getting illuminated? The southern hemisphere. The northern hemisphere is pointed away. So our seasons are the result of that tilt of Earth's axis. That axial direction stays the same no matter where it is in its orbit. And the seasons, the hot and cold parts of our seasons, all depend on how directly the sun hits the surface of our planet. Sometimes I can pull this off. You guys see the light on my phone, right? Okay, turn it back on, right? Let's make it nice and bright. Okay, so you see that, right? Okay. It's kind of hard to see on this board, but if I hold my light directly in front of the board, can you see the circle of illumination? Okay. Now what happens if I tilt it? Does it look as bright? No. It spread the same amount of energy over a bigger area. That's what's going on in the wintertime. Okay? In the wintertime, the sun, from our point of view on the surface of planet Earth, is kind of low in the southern part of the sky. And so the sun's light isn't coming directly down at us, it's coming at an angle. And it just feels colder. The sun hasn't really changed its distance. I mean, we're a little bit off, right? But not by much. And it's not like somebody turned down the thermostat. It's just the energy, which is constant coming from the sun, is getting spread out over a bigger area as it impacts during the wintertime. As we go towards summer, though, the sun, from our point of view, will look like it climbs and ends up like basically directly overhead. Okay? And that's just like a blowtorch coming down in Fresno, isn't it? Okay? So that's why you have seasonal variations. The tilts of the Earth axis, not where it is in its orbit. Because actually in our winter, we're 86, 87 million kilometers from the sun right now. And we go out to a maximum of like 93, or no, that's the average. We go out to a maximum of 98 or something like that. So there's variation, but on average, we're 93 million miles, kilometers, some unit. It's a big number away. All right, so that's Kepler's first law. The orbits of the planets are ellipses. That's really what you have to take from that. Learning the reason for the seasons was a bonus. Added extra. You didn't have to pay extra for that one. All right. Kepler's second law is the equal area in equal time law. What the heck does that mean? So I'm going to use a bigger version of what I did up there. So we've got this ellipse, right? And we've got the sun, and we've got like a planet, right? going around the sun. Doesn't have to be Earth. What Kepler found out is that if you draw like an area, draw like a pizza slice, okay? You calculate this area here, which is bounded by an arc over here. So like the planet starts down here and is going around and goes to the other point in its orbit. And you take and you bound that at the sun or the focus, right? And then you go and you find exactly the same area but somewhere else. This isn't to scale, but let's say we just do like that, right? And we calculate the area. The areas of those two blue segments are exactly the same. And what Kepler discovered is that the planet will pass along this arc, okay, that's bounded by that area in exactly the same time. It has to be moving faster when it's closer to the sun. So what this means is the orbital speed isn't constant, which makes sense because it's an ellipse. It would be constant if it were a circle, but it's not. It's an ellipse. And therefore, planets move faster when they're closest to the sun and slower when they're further away. We haven't talked about it yet. We haven't talked about conservation of energy yet. That's next chapter. But what Kepler discovered about 50 years, 100 years before we could give it a name, he discovered conservation of energy. He just did it in this area, and equal times, meaning that orbital velocities are different. So where is it fastest? Closest to the winter for Earth, right? Okay. Curiously enough, planets have different tilts to their axes. And is it, I think it's Neptune. Neptune's orbital rotational axis is 90 degrees. So it rolls around its orbit. Okay, it's kind of fun. So one of its sides is basically always pointing. So it's permanent summer on one side and permanent winter on the other. All right, third one. This is the one with meat in it. Let me get the way your book writes it. It's the period or time it takes for a planet to go around the sun. It's 2 and pi. What's 2 pi doing there? Circles. By the way, this is the circular version, not the elliptical version. Kepler did the elliptical version. Okay. What's r? The orbital radius. So this again would be center to center distance, right? Center of the sun to the center of Earth. Center of the Earth to the center of the moon, right? You've got to go center to center distance. To the 3 halves. Sorry. Divided by the square root gets worse. A big G times big M. What's big G? The gravitational constant, right? 6 point, whatever it is, times 10 to the minus 11. Okay. What's big M? It's the mass of the thing being orbited. So Kepler's laws apply to any orbital body. It can work for the moon. It can work for satellites. It can work for the International Space Station. It can work for the Hubble Space Telescope. It can work for the James Webb Space Telescope. Whatever object is in orbit, it has to be orbiting something. So the big M in this equation is the mass of the bigger thing. It's the mass of the thing being orbited. So if we want to calculate the orbital period of the moon, what mass do we put in there? Earth. Okay. If we want to calculate the orbital period of Venus, the planet Venus, what mass do we put in there? Good, the sun. If we want to calculate the orbital period of Io, which is a moon of Jupiter, what do we put in there? Jupiter's mass. You getting the idea? That big mass is the thing being orbited. You're calculating the orbital period, the time it takes for something to orbit of the satellite or Io or Venus or whatever, but the mass that goes in is the mass of the thing that's being orbited. I'm not sure how to say that any clearer. What Kepler was after was a nice, simple relationship. What he wanted was like, so how long does it take the Earth to go around the sun? 1 year, right? Okay. Mars has an orbital distance from the sun that's roughly twice as much as Earth's is. So wouldn't it be nice if a year on Mars was 2 Earth years, right? It's twice as far, so 2 Earth years. Jupiter, it's about, what was it, about 6 point something the distance from the Earth, right? Okay. Wouldn't it be nice if it's year? That's not how it works. Okay. It takes Jupiter about 10 years to go around the sun for every 1 Earth year. And Jupiter is certainly not 10 times further away. So Kepler was looking for a nice, even relationship, but this is the one that nature gives us. Okay? It's r to the 3 halves. What does r to the 3 halves even mean? What's any like half? If you take, what's 4 to the half power? That's 2, because a half is a square root. It's like a shorter way of writing a square root. Okay? So raising something to a half power is like taking a square root of it. It's exactly the same. So 3 halves means what? You cube it, and then you take the square root. If you don't like this, take it up with the maker. Okay? Because this is our observation of it. The elliptical version, it's worse. Okay? So let's use this, Kepler's third law, okay, to calculate something. So I'm showing you a picture here of Alpha and Beta Centauri. Alpha Centauri is the star that's closest to our own. What's the closest star to Earth? The sun, right? Okay. Outside of our solar system, the closest star to Earth is Alpha Centauri. Alpha Centauri is about 4 light years away. It's our closest neighbor. That means it would take light, the fastest thing in the universe, 4 years to get there. Okay? This is just me flexing now. Does anybody know what the fastest man-made object is? Usain Bolt. Depends on, I guess, how you define man-made. It's the Parker Solar Probe. Yeah, nobody knows that, right? Okay. Parker Solar Probe is in orbit around it's a solar probe. It's around, orbit around the sun. It actually takes dives into the sun's corona. And it does that by doing huge elliptical things, right? It goes way out and then it comes way in. But because it's elliptical, it doesn't spend very much time in the corona, because if it did, it would just burn up from the heat, right? So it does these dives. And it moves at a speed, I don't remember exactly what the number is, but it could get, the Parker Solar Probe can get from the Earth to the moon in about 3 hours. Okay? Like it's moving really fast. I might even be wrong there. It might have been 30 minutes. It had the number 3 in it. It's going fast. It's the fastest object that we humans have ever made. If the Parker Solar Probe was sent to Alpha Centauri, it would take like 30,000 years to get there. Okay? Yeah. Like we need warp drive yesterday. Right? By the way, physicists have figured out warp drive. We're just waiting for the engineers to catch up. Warp drive is really simple. Okay? This is how you do warp drive. Take the energy of the entire universe and shove it into a space roughly the size of a 2-liter bottle. That's it. That's all you need to do. Engineers keep complaining about, well, we can't get that energy, or we don't know the size of the water bottle, or whatever. We're like, those are details. We figured out how to do it. Figure it out. Of course, it doesn't really help, okay? So in the Alpha Centauri system, there is a planet called Proxima Centauri, okay? And I went and pulled data, okay, about Proxima Centauri b. This is the planet around this star, okay? We are in a spaceship, hopefully. Every spaceship needs a name, doesn't it? Yeah. What's the name of our spaceship? SS Balogh? I can live with that. Okay? So we're in the USS Balogh, right? Okay? For some reason, the USS Balogh was not equipped with a basic computer to just tell us. It can tell us our orbital period. it can tell us the distance between us and the core, but for some reason it can't just do the mass of Proxima Centauri b, right? Okay. So we're going to calculate the mass of Proxima Centauri b for the computer. You can tell this is a made-up problem. I did pull the data that we have, right? Like we are able to measure the period from Earth using telescopes and things like that, okay? So the period is 1.57 Earth hours, according to Wikipedia, okay? And then I chose a distance of 7,500 kilometers, okay? I want to point out a couple of things here, like in our visualization. We'll start with the visualization, okay? So here's Proxima Centauri b. There's the planet, right? And our spaceship, which again looks like a TIE fighter, right, is in orbit around, okay? Notice we were given two numbers, 7,500 kilometers and 500 kilometers. What does this word right here mean?
Acceleration.
Nope. What's an altitude? Distance from the surface. Okay? Altitude means different distance from the surface of something, not the center of it. And remember, it's the center to center distance that's the important one in Kepler's laws. So that's kind of a trick, right? The altitude of our spacecraft is 500 kilometers. So if our center to center distance, right, they told us the total distance between the ship and the planet's core is 7,500. What does that mean the radius of Proxima Centauri b is? It must be 7,000, right? So that's what's going on there, right? This distance right here is 500 kilometers. But the distance from there to there, again, this is not the scale, is 7,500 kilometers. So watch out for that terminology, because it can kind of trip you up. Okay, what do we know? Let's make a list. We know the period, 1.57 hours. We're going to use Earth's unit system. We also know the orbital radius, 7,500 kilometers. Do you guys, do you feel comfortable with those numbers? Well, you shouldn't. Because what's wrong with them? The units, right? What units do they need to be in? They need to be in seconds and they need to be in meters, right? Okay, so 1.57 hours. For every 1 hour, there's 3,600 seconds. I got 5,667 seconds when I converted that. And then how do we get kilometers into meters? Kilo literally means times 10 to the 3. So you can just write 7,500 times 10 to the 3, and you'll get the answer in meters. All right, so we got those converted. So they want to know the mass of Proxima Centauri b. Well, what we have is Kepler's third law. Can we use it to find the mass of the planet? Do we know the period?
Yes.
Yep. Do we know the orbital radius?
Yes.
Yes. So what are we solving for? Big M. Oh my gosh. How do you get big M out of this thing? Okay, you want to multiply first? Sure. T times the square root of jig g m equals 2 pi r to the 3/2. So I multiplied both sides by square root of gm. But to get the m out of the square root, what do we have to do? We got to square both sides, right? So this is t squared times g times big M equals 4 pi squared. Oh, and then r to the 3/2 squared becomes just r cubed, doesn't it? That's nice. So that means my mass is going to be 4 pi squared r cubed all over big G t squared, assuming I did all of my algebras correctly. So now I got to put in numbers, right? 4 pi squared are numbers. And then my radius, 7,500 times 10 to the 3 cubed. I wish you the greatest of luck getting this stuff in your calculator correctly. You are going to be in parentheses hell, right? So be careful. Or use Desmos or something, okay? Which is not available to you on the exam. Big G, 6.67 times 10 to the minus 11. And then 5,667 squared. It's a lot of stuff to put in the calculators, but once you do it, you get 7.77 times 10 to the 24 kilograms. Earth's mass is 5.97 times 10 to the 24 kilograms. So who weighs more? Proxima Centauri b weighs more, okay? But not by much, right? It's only like 10% bigger or something, like 10% more mass. All right. So that was the mass of Proxima Centauri b, the mass of the planet. And then they ask us a second question. So now we've brought something with us that weighs 560 newtons on Earth. And we want to find how much it weighs on the surface of Proxima Centauri b. Well, what's weight? Yeah, weight, it's part B. Weight is mass times little g, right? So the weight changes. Whether you're on Earth or Proxima Centauri b, the weight's going to change. Why is the weight going to change? Because little g is going to change, right? And we know that little g is gm over r squared. Yes. So what's the thing that is not going to be different, whether this object is on Earth or on Proxima Centauri b? Mass. It's the mass. So if we solve for that mass, it's going to be the weight divided by gravitational acceleration on Earth. Then I can do 560 divided by 9.8, which got me 57.1 kilograms. That 57.1 kilograms is going to stay the same, regardless of where it is in the universe. So now I'm going to find little g on Proxima Centauri b. Well, that's big G times the mass of what? What object? We're looking for little g on the surface of Proxima Centauri b. So what are we going to put in for big M? The mass of Proxima Centauri b. All divided by the distance to the surface. So what is this going to be? This is going to be 6.67 times 10 to the minus 11 times our mass, 7.77 times 10 to the 24, all divided. And what's the distance to the surface? Center to the surface of Proxima Centauri b? 7,000. 10 to the 3 squared. When I put that in my calculator, I got 10.6 meters per second squared. Okay, so how much stronger is gravity on Proxima Centauri b? What's gravitational acceleration on the surface here, planet Earth, right now? 9.8. What is it on Proxima Centauri b? 10.6. So basically the same. A little bit bigger. If you went for a walk on Proxima Centauri b, after about a half hour, you wouldn't know the difference between that and Earth. Your body would adjust to it. Okay? So it's pretty much like a close Earth analog in terms of that. How do we find the weight on Proxima Centauri b? Yeah, it's mass times the gravitational acceleration on Proxima Centauri b. So 57.1 times 10.6 gets me 604 newtons, or about 136 pounds. So it was 126 pounds on Earth, and it was 136 pounds on the surface of Proxima Centauri b. Not to burst your bubble too much, but all we have are artist renditions of Proxima Centauri b. It just looks like a fuzzy dot in the telescope data. Proxima Centauri b appears to be tidally locked to its parent star, meaning that the amount of time it takes for it to rotate around once on its axis is exactly the same amount of time as it takes to go around its sun one time. So that means one face is constantly facing. Our moon is tidally locked to us. We always see the same side of the moon when we look up at like a full moon. That is a problem because that means there's uneven heating on the surface. Proxima Centauri b is close enough to its parent star so that it is bathed in radiation. And so chances for life to be there, pretty darn small, in as much as we understand how life works. And we haven't detected any breathable atmosphere. It's like a carbon-nitrogen atmosphere, and it's very, very hot. Like hundreds of degrees Celsius on the surface. Okay? So not even a really nice place to visit, let alone try to terraform.
What's the denominator for the last equation?
It's 7,000 times 10 to the 3. Yeah. We wanted to know what this thing weighs on the surface, right? And so we needed the surface, the distance from the center to the surface, not where we were in orbit. I should probably clean that up just a little bit to make sure. Everybody can read it. Okay, there we go. I want to show you a video. This one I actually pulled up on the computer because I could find it really quick. The video I want to show you comes from SpaceX. And I want to be very clear, this is not an endorsement of Elon Musk, who I think is a terrible human being. However, SpaceX, Neuralink, Tesla, these companies are doing a lot to change the world and our quality of life. And the SpaceX engineers about 8 years ago put out a video. And this video is entitled, How Not to Land a Rocket Booster. And I want to show you this video. And I want you to watch and notice what happens during the video for all of their attempts, because it teaches us an excellent lesson. Oh! How do you learn how to land a rocket? keep doing it and learning from your mistakes. How do you learn physics? Remember how I told you? You need to learn how to fail and fail quickly, right? SpaceX is launching hundreds of rockets a year now, recovering those boosters, turning them around in a matter of days, and launching again, right? We went from launching maybe 5 or 6 rockets a year, right, to launching hundreds of rockets a year. NASA's approach before SpaceX and other companies like Blue Origin was to make sure everything was perfect before you launched, right? But it still wasn't perfect. We have 2 space shuttle disasters that took human life from us as proof that you can try to be perfect and still not make it. SpaceX took a different route. They decided to try, see what happened, make a change, try again. SpaceX came this close to not making it, but they did. And now they are putting more mass into orbit than all the other companies and countries combined. We are living in an unprecedented age of rockets delivering stuff to space. And it was brought to you by the same process that I've been trying to teach you all semester, right? Try, keep trying, keep failing, keep learning from those mistakes, and try to start sticking those landings, right? You want to stick the landings before the exams, right? Okay, that's kind of the whole point. Artemis 2 is going to launch, like I said, sometime in March. This is NASA's attempt to get humans to orbit the Earth. By all accounts, it's going to be a nice, safe ride, and they've got lots of stuff to do on that. I think it's like a 14-day mission in a capsule that's basically the size of the inside of a minivan. Can you imagine being in there with 3 other people and a toilet in 0G? So that's going to be their fun. But we're going back to the moon. SpaceX has got their super heavy booster that they've been testing. You may or may not see in the news about how yet another one blew up. Okay? It's not the explosion that matters, right? What matters? It's the trying, right? It's the data you get along the way. Because as SpaceX has shown, if you get the right data at the right time, it can make all the difference to a successful product. That's all I've got for you for Chapter 5, and we'll just leave it there, okay? You got my announcement about you guys get to grade me this semester. Did you see my announcement about my evaluation? Okay, so just keep an eye out for those emails. And then no grass tomorrow, and campus is closed tomorrow, Monday. Okay? Have a great holiday weekend.